So chapter 7 is covering various shapes of graphs that we call conic sections. The idea behind that phrase, conic section, this image here kind of summarizes what we're going to be looking at. We've seen a circle several chapters ago, which we'll slightly revisit, but we're going to focus on these other three shapes. The idea of taking this particular shape here, a right circular cone, and using different planes to kind of intersect it and seeing the shape that we get. Notice that if you take a cone and cross it kind of what you could call perpendicular to the cone, you get a circular cut. But if you were to angle that plane, you would get an elongated, or what you might kind of call an oval cut. Now, if you were to cut it in a way that it is actually going parallel to one of the kind of angles or sides of the cone, then you would get this shape along the side here, creating this shape that we know as a parabola. And if you were to cut this cone vertically, you would get both a shape up here and a shape down here, and this is referred to as the hyperbola. So these three are going to be the next three conic sections that we take a look at. Now, this is one way to define them or describe them or visualize them. Another way, as we start to focus in on the ellipse in this section, another way of defining an ellipse, the set of points on this, again, you can call it an oval, they are actually the set of points such that if you look to the center of this ellipse, and then there would be these 2 points that we call the foci or foci, which is the plural of focus. So one's a focus, but two or more is a foci or foci. There's these 2 points that exist in this, within this oval shape, that every single point on this oval, on this ellipse, is the same total distance from the 2 foci. Meaning if you added up this distance and this distance, you get a certain number, and you would get that same number no matter what point along this ellipse you looked. It's almost like thinking if you had a piece of string attached to these 2 points and you stretched it tight, and then you just kept pulling it tight and seeing where your pencil went as you pulled it tight against those 2 points. The same distance, that string's length doesn't change, just where you want that point to go, you'd create an ellipse. So that's an interesting factor construction for ellipses. So as far as classifying them, we essentially just classify them based on which way they're stretched further. We can see ellipses stretched left and right, in which case we call that a horizontal ellipse. We can see ellipses stretched further up and down, which we call vertical ellipses. Now, with those stretchings and orientations, the terminology we use the phrase major axis, minor axis, and then we just mentioned center earlier, to represent which of the 2 directions is the longer stretch. So the major axis is the one that is major, bigger than the minor axis. So for a horizontal ellipse, the major axis is the one going left to right, the minor axis is the one going up and down, and vice versa for the vertical ellipse. Now, what's important is on this ellipse, we could say there's these 4 points, but only 2 of them really get the specification or the name of vertex or vertices. And those are going to always be the points on the major axis. So for a horizontal ellipse, your vertices are these 2 points. But for a vertical ellipse, your ellipses are these 2 points, or your vertices are these 2 points. So make sure you kind of understand the difference in which points are labeled the vertices, because these points are not and these points are not for the given ellipses. But now to look at the formulas we need here, looking at what we call the standard form of an equation of an ellipse. So you'll notice you've got the x squared and y squared quantities here, but then underneath them is going to be an a squared and a b squared, or basically we'll see a number. The idea is this a and this b, if you look down here, the a and b describe the distance left and right of center that you have to go to get to the points of the ellipse. So if here's your center, and these are both centered at 0, 0, on the next page we'll see what happens when you have to shift your ellipse off of the center there at 0, 0. But notice a, so from 0, a is always paired with x, and a tells you how far left and right you would need to go, the distance from 0, from the center, to either side, left or right, horizontally. Just like b will tell you the distance vertically to get to your values on the y-axis. And that works either way. This book uses a difference here with the b and the a. They put b under x and a under y. I'm almost not a fan of this. I guess you need to be aware of this when looking through my math lab. just to understand that they're always putting A with the major axis, right? A was for X because it was stretched horizontally. Here, A is with Y because it's stretched vertically. There's pros and cons to that, so I'm not going to say that in this case A and B to me make all the difference in the world other than you just knowing the roles, right? Whatever number is below the X tells you X. Whatever number is below the Y tells you horizontally Y. I'll say that for sure. Now, the C is important. There's a C here, and the C is telling you the distance to the foci, right? Distance left and right in this case for horizontal, or distance up and down for vertical. So the distance C to get to the foci, you'll notice that's not in the formula anywhere. It's not going to be in our equation. We have a specific foci formula there. So that's going to be the formula we would use once we have A and B to calculate the value of C to figure out the distance to the foci. So the next page gives us a rundown of what our formulas will look like when they are shifted, and the only difference here is that you'll have a minus h and minus k within the squared quantities. So think back to when we did things like working with circles or even other transformations. This case where you're working inside of these parentheses, notice the h and the k are being subtracted. So whatever number you see in there, you kind of have to think opposite. And we'll get into some examples of that in the following pages in the next video. But that's the idea. Just to shift the center is to have to throw in an h and k into our equation of our ellipse. Other than that, everything else shifts with it. So no other real changes there. We'll see those as we get to an example. And so for one quick example of a centered at 0, notice I say it's centered at 0 because I see just x squared and y squared. No pluses or minuses there. So I'll even point that out as that will change as we move on to the next pages. Center of 0, 0. And so I'm going to call that a squared and b squared and pertaining to the x and the y. So if a squared equals 9, well then a equals 3. And if b squared equals 4, then b equals 2. And so if we're centered here at 0, 0, a is the distance associated with x, so left and right 3. B is the distance associated with y, so up and down 2. And that's it. That's all we need to sketch the graph of our ellipse.